on synchronization of oscillators and active matter. And indeed, today's talk is about synchronization and extensions of the Kuramoto models for coupled oscillators. So please, Guilherme, the stage is yours.
Can you hear me well? Okay, thanks Dario for this nice introduction. As he mentioned, I'm a postdoc here. I will talk about extensions of the Kuramoto model for coupled oscillators. You can interrupt me at any time for questions. So let's start. A brief outline of the presentation. First, I will give some examples and introduce the core concepts on synchronization. Then I will discuss the principal model on synchronization of oscillator, which is the Kuramoto model. Then present some interesting extensions, focusing on this matrix coupling, which is the model that I currently work, and then I will draw some final remarks. Okay, so starting on the introduction, like a lot of concepts in physics, synchronization, and the word synchronization comes from the Greek, in which syn means together, and chronos means time. Like in joining these two together, we have a meaning about passing more time together. That is what synchronization means. And we do not have a formal definition of synchronization, a mathematical definition, but Stephen Strogatz, which is perhaps one of the most important researchers on synchronization, wrote in his book, Sync, that synchronization is a process where, due to their interactions or to an external driving force, dynamical systems adjust some properties of their trajectories so that they eventually operate in a macroscopically coherent way. So we have several elements on a system, each one with their own dynamic, and they will interact in some way in order to adjust some of its properties. And here we are interested in analyzing systems that have a periodic motion or periodic behavior, which constitutes an oscillator. Okay, have a lot of examples of both natural and man-made systems that have synchronization. Perhaps the most widely known is those of the fireflies flashing in a dark night. Mainly in Malaysia, there are some forests that are extremely dark, and then the fireflies, they communicate, they flash all in sync during certain seasons of the year. We also have another important synchronized system, which is the cardiac pacemaker cells. Now the cells of the heart, they need to pulse in synchrony in order for the body to work. We also have the neuronal firing. The activation, charge and firing of neurons need to have a certain degree of synchrony in order for the electrical signals to be transmitted. But in this case, we do not want a global synchronization associated with all neurons firing at once, because this is associated with epilepsy. So we have certain systems that we want certain degrees of synchronization, and other systems that we want global synchronizations. Okay? We also have laser pulses, which the atoms that will produce the photons, they need to emit those photons in synchrony in order for the laser to have a current light. We have some astronomical systems like the tidal locking of astronomical bodies, the rotation, the spin-orbit coupling between the moon and the Earth, maybe considering an example of synchronization phenomena due to gravitational locking. We also have power grids, and a particular one that I like are those of circadian rhythms, that are several biochemical processes on the body that have a period of 24 hours. So a lot of processes that occur on the body has this period of 24 hours. We can say that all these processes are in sync with the rotation of the Earth. Okay? Well, the earliest known description of spontaneous synchronization is due to Christian Huygens in 1665 in a letter that he wrote to his father, describing what he says as a node sympathy between two pendulum clocks that were supported in a wooden bin in his room, And he noticed that these clocks were ticking in unison, in perfect antiphase unison, which is kind of curious because due to the technology available at the time, no two clocks have perfectly matched frequencies. They have always have some deviation, so this synchronization is a curious phenomenon at that time. And he postulated that the sympathy occurred due to imperceptible motions of this wooden beam. In some way, energy and momentum will be transmitted to one pendulum to another by this beam. And although he could not prove or formalize the mathematical theory behind this idea, his intuition was right. They will prove that this is really what happens in the last century. And although it's a problem from 1965, there are papers from 2 or 3 years ago that describe apparatus similar to this one, describing this kind of synchronization. So it's, despite an old problem, it's also an actual area of study. And what I will, yeah, it's really complicated.
So what's the why antiphase? Because I think the system should tend to the minimal energy of the normal modes.
Yeah, inclusive this is a question that they do not know until now. Why this is happening in antiphase? Because we expect that they would synchronize in phase with each other.
Which is the minimal energy of the normal mode, right?
They could not replicate exactly what are the necessary conditions for this antiphase synchronization to occur.
I see.
Even today.
Okay.
So we have a system here that I call a Huygens-like experiment, but instead of using pendulums, they use metronomes to illustrate what possibly happened in the case of Huygens. Let's see if I can play. Each of these metronomes has a frequency, and they are taken in their own frequency and phases, and having a supported beam. And once I support all the system by 2 cans in order that the movement of the pendulums can displace the board, they transfer momentum between the system and they start to synchronize after some time. Okay? I'm really happy that this video does not have sound because the ticking is really annoying when they are not synchronized. So this is probably similar to what happened in the Huygens experiment. Now we can start to talk about the Kuramoto model itself. It's a relatively simple model that was proposed in 1975, in which a population of N oscillators, everyone described by a phase, theta, they have a certain natural frequency, draw for a given distribution, and we couple these oscillators in a certain way. In the case of the Kuramoto model, is a sinusoidal function that acts like a species of mean-field interaction between all oscillators. And we have the coupling parameter that quantifies the intensity in which one oscillator influences another. And in order to quantify the degree of synchronization, we use the complex order parameter Z. That is basically the sum of the phases. And as we change, we vary, okay? We can obtain 2 different states. If this coupling is small, then each oscillator have their own dynamic. They will not be able to influence the other oscillators. The module of this order parameter will be close to 0. But then after I increase this value, the system undergoes a second order phase transition.
Sorry for interrupting. Is there any physical system that is well described by this particular equation? Or this is a mathematical, the motivation is mathematical?
Yeah, the motivation here is purely mathematical.
Okay.
In this case, because although it's an area that is very well developed in terms of mathematical models, it's extremely difficult to measure what would be the equivalent to this K, for example, for fireflies. How can you measure, for example, how one firefly influences the other? these are kind of systems that are being studied really recently in centers of collective and animal behavior, for example. In this case, you can construct certain systems, but extremely artificial, in which they work like this. Okay. There's a certain range of parameters that the metronomes that I show can be approximated by equations like this. Okay. So here we continue. We have a second-order phase transition here, in which if we increase the coupling, then the system starts. The motion of the system starts. Can be described in a coherent way, in a more synchronized state.
Sorry,
Okay.
I also have a question, because here, I would say when they are, I don't know, maybe I'm wrong. When they are synchronized, you say that all the theta j become equal to each other, right?
This is one way of synchronization, but they can adjust their frequencies. It's also considered synchronization. You have phase synchronization,
Okay.
in which they adjust their frequencies in their phases, and you also have just the phase synchronization.
Okay, but in this plot, you are looking probably for the phase, right? Because the phase goes out, and then you get 1 over n times n, so they cancel, right? And probably you are removing... no, wait, because this is a complex... Okay, got it, yes.
Okay. Okay, any other question? Yeah. Exactly.
Let's keep two microphones, one here, one there.
Okay, so here we have some GIFs to illustrate what really happens in the system. In particular, we have another assumption here for the distribution of the frequencies to be symmetric and unimodal. In this case, when we have a k smaller than a certain threshold, the system is the current. Here we are plotting all the phases with modulus 1, and each one have their own dynamic. But once I have passed this threshold, the system starts to cluster together and move as a pack. And this pack rotates with the average frequency distribution.
So, okay, you will tell us what this K means. I mean, it's...
This K is the coupling between the oscillators.
Ah, the coupling
before. It's this K here. Okay? So since the synchronized pack rotates with this frequency, usually we set this average to 0. Then when we have a synchronized motion, all particles, they are close to a certain theta. And this theta is random, depending on the initial conditions, because the system has a rotational symmetry.
And here you are considering the model all-to-all.
Huh?
Here the model is all-to-all.
Yeah, this is exactly this case. We have a population of n oscillators, and all of them are connecting with another.
What in your system gives you the scale of Kc? I mean, in this particular case, what's the value of Kc?
Okay. I will show you in the next slide how we can start to treat this equation in a more formal mathematical way. Okay. For this, we use the technique called dimensionality reduction, in which the goal is write dynamical equations for the order parameter z, which is this equation here, instead of having individual equations for each oscillator. Okay, so we are trying to describe the system in terms of the order parameter. For this, we will consider a function that is the density of oscillators. Because there are no destroying nor creation of oscillators, we have a continuity equation. And we will use the Antonsen ansatz, that is a specific way to expand this density of oscillators in terms of a Fourier series that depends only on the powers of a single parameter. Okay? So it's an ansatz because it's not a mathematical proof that this is the only possible expansion, but it's possible to prove that this form satisfies the original Kuramoto equations. So by performing this expansion and done a lot of calculations, we can write the equations for Z for 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 a few particular cases of frequency distributions, because we need to solve an integral that can only be solved if this distribution is uniform, a delta, or a Lorentzian distributions of frequencies. Okay? In this case, we can solve these equations analytically. I will not take into detail here, but you can write dynamical equations for the module and the phase of the order parameter, in this case, in which delta is the shape parameter of the distribution, and omega 0 is the average of the distribution. And these equations we can analyze in terms of non-linear stability, find the stationary solutions, and see in which values of the parameter k the trivial solution loses stability, which is exactly when this value here is 1. Okay, so this parameter is 2 times the width of the distribution frequencies. The critical value for the transition would be this. Okay? So this is how we approach this kind of system. We can also perform numerical simulations, but in terms of a mathematical and analytical treatment, we basically use this Antonsen ansatz in order to write these equations and then perform linear stability analysis to see when the system will synchronize and when they will stay disordered. Okay? Well, this is for the Kuramoto model. Let's discuss some extensions and generalizations now. And it's interesting to note that we can have a lot of paths to take from this original model. We can, for example, instead of consider all-to-all interactions, we can think of structured interactions. For example, a lattice, a graph, a complex network, a hypergraph, in which I have a certain patterns in the connections between the oscillators. We can also add a delayed coupling that in a way that the signaling between the oscillators is not instantaneous. We can work with non-usual frequency distribution. And by non-usual, I am thinking about bimodal distributions. A certain group of the oscillators have a certain distribution, another group has another, and then you see how they interact. We can also consider high-dimensional oscillators with more degrees of freedom, with more rotational degrees of freedom. We can also add external driving, or even couple an oscillation with movement in the systems in which we call swarmolators. So there's a lot of paths that we can take in order to extend and generalize this model to add new ingredients in order to describe even more complex synchronized behaviors. Okay? So the first one that I like to discuss is the Kuramoto with structured interactions, in which this is usually made by adding an adjacent matrix here that indicates which oscillator is connected with each one. This Aij is 1 if oscillator I can see oscillator J, and 0 otherwise. And by writing this matrix, we can represent, for example, d-dimensional lattices or complex networks. And in the case of d-dimensional lattices, we can calculate the lower critical dimension in which the global synchronization can occur. And these dimensions, it's 2 if we are considering frequency synchronization, because each oscillator have different frequencies. If they adjust only the frequencies, it's called frequency synchronization, but we have a stronger form of synchronization that instead of just adjusting their frequencies, they also adjust their phases. So it's more difficult for the phase synchronization than the frequency synchronization, and this can be seen in the lower critical dimension being lower in the case of frequency and higher in case of phase Okay? We can also analyze what happens when we have complex networks that for terms of dimension, they are equivalent to a system with infinity dimension if the network is a small world. And here we add another ingredient in which we are correlating the degree of the nodes with the frequency in order that such as the vertices with more connections, they rotate faster. And if I assume this, then the transition can become explosive and become a first order, a discontinuous transition, in this case, which is a novel behavior that can only happen in this kind of system. The other graphs are complex networks that are not scale-free. So here we have a scale-free network in which this transition can occur, and the other we have random networks in which we do not see this kind of phenomena here. Okay? We can also add the coupling delay, as I mentioned, which is called the Kuramoto-Sakaguchi model, which was proposed in 1986, in which I have another parameter here that is associated with the time that a signal takes from one oscillator to another. We can also construct the equations, analyze the stability of the solutions, and discover that the critical coupling is now 2 delta over cosine alpha, which implies that this alpha is great enough, then you cannot have synchronization in some cases. If the signal took too long to propagate from one oscillator to another, then you cannot synchronize. And this is what this graph is showing. For alpha equals 2, then you always have this disordered behavior.
Sorry, the fact that this curve is, let's say, the critical kappa, whatever, everything is independent on n, it's a property of the fact that you are all-to-all, I guess, right?
Yeah, we have a...
Because I would tend to guess that synchronization is a global phenomenon, it's not local.
Yeah.
So
in this case, we have we always have a finite side scale in this case because this is a simulation of the individual equations. But if we took if we analyze these equations here, which are assuming the thermodynamic limit, then you will see a transition in a more formal way. The curves, they are kind of ugly because these are simulations that I...
No, but yeah, the question was more like Kc is just a function of delta and alpha is not a function of n.
No.
And that I was asking, is a property of the fact that the graph is all-to-all? If the graph is not all-to-all, probably you will have a dependence on n as well.
Yeah, you can probably depends on the momentums of the degree distribution.
Because, yeah, my guess is that synchronization is a global phenomenon, it's not a local thing, so it matters n. The fact that n here doesn't matter, I was wondering maybe is a fact that everybody, let's say, directly is connected with everybody else, but
yes.
Maybe not. Okay.
Exactly. Okay, so we can discuss other types of extensions which are related to external drives. So we have some systems that we want to add a certain external force, and we want to see what this external force will do to the synchronized state. So this is a little different because I am not interested in see how the synchronization of the system will be changing. For example, okay, I have a system that have their own synchronized movement, and I will add these external forces to see if this external force can change the synchronized behavior or the system will not see this. In other words, I want to see if the system can synchronize to the external force or if they can keep their own motion, even in the presence of this external force. Okay? So we have the intensity F and the frequency of this external drive. We can also write equations. They are becoming progressively more complex, but this can still be analyzed. We can make a change in the reference frame to eliminate the explicit dependence of the time here in order that these equations are still autonomous. You can analyze the fixed points. The bifurcations here are more complex, but what is important is that this region A and D, which is the upper triangle of this graph, the system synchronizes with the external forces. So it does not matter how the dynamic will be, the system will act as a part of this external force. But in this lower part here, this E region, the system will maintain their original dynamics and the external force will basically do nothing in this case. Despite some technicalities or bifurcations that are more complex, this is what happened. A and D are regions in which the system synchronizes with the external force, and the E is the region in which the system stay with their own dynamic. And this diagonal is exactly x equal y. So it's a relatively simple result, simple and important result here. Okay. This is not necessarily an extension or adding more ingredients to the Kuramoto model, but just another formulation of the problem itself. Because in the other equations, we are constructed the dynamical equations in terms of phases. But you can think of this phase as a vector rotating in a plane or in a sphere. So we are substituting the phase for a vector and write this equation in a vectorial form like this. This is exactly the same equation as the original Kuramoto model that I showed you early, but now using this sigma which describes each oscillator. It's considered like a vector that rotates on a circle. And what is interesting in this formulation that is surprisingly recent, 2019, it's now I can think on this equation is not restricted to two-dimensional vectors. I can, for example, have a three-dimensional vector rotating on a sphere. So I can add new rotation degrees of freedom to the system and extend it to 4, 5, 6 dimensions, any number of dimensions I like, for the oscillator, which is different from the way that I arrange the oscillators, which would be the space dimension of the system. So the oscillator can have a dimension associated with the number of degrees number of rotation degrees of freedom that I have, but I can also arrange it like a square lattice, a cubic lattice. These are different things. Okay, and when I write the Kuramoto model in this vectorial formulation, the frequency, the natural frequency, we need to be write as an antisymmetric matrix. And the order parameter now would be just a sum of the individual vectors, the center of mass of the individual vectors, and I will, from now on, start calling the order parameter P instead of R. Okay? And when we perform the stability analysis on the system on several dimensions, we observe that for all dimensions, the transition is continuous, and for even dimensions, the transition is continuous. So if this oscillator is a vector on a circle, the transition is continuous. If this is a three-dimensional vector oscillating on a sphere, the transition is continuous. In 4 dimensions, it goes back to be continuous, and so on. Okay? So these are the different ingredients that we add in the Kuramoto model. Now I will discuss the model that I work, which is the matrix coupling Kuramoto model, in which we have let's say, a lot of those ingredients in the same model. Because of the vectorial formulation here, we can extend the coupling. The coupling is scalar to a matrix. Instead of just a K, we have a matrix K. And we can allow more complex coupling between the oscillators than just a simple scalar. We can parameterize this matrix in 4 parameters. We can write it like this, as a rotational matrix plus a symmetric matrix. And this is a convenient way to write this matrix because I can recover the original angular formulation like this. If I write at principle, I can simply write this matrix as 4 independent entries. But if I parameterize the matrix like this, we can write back the equations in the angular formulation that looks like the original Kuramoto model. We have here the component that is associated with the Kuramoto-Sakaguchi model, and then this term of frustration here. So it's easier to convince that this is indeed the original Kuramoto model if we write the matrix like this. And what this matrix coupling introduces in the system is two new forms of synchronized states. At first, we have these blue regions here, which is the usual decoherent motion. So in this region, the system stays, each oscillator stays with their own motion. But we have two new synchronized states, which is the phase tuned in green here, that all the oscillators, they go to a certain preferential direction, and they stay locked on onto this direction. And this direction is the dominant eigenvector of this matrix. So due to this J parameter, the system now do not have rotational symmetry because we have a preferential direction that the oscillators tend to cluster together. So they cannot cluster in any angle. We have only two spots that the oscillators will tend to cluster in this green region. And in the red region, we have what we call the oscillatory states, that in which both the module and the phase of the order parameter oscillates in time. In the next slide, I will have some examples that will make the difference between these states more clear. But other thing that is important in this model is that it reduces to several previous models that I showed early. We have in this red diagonals, the model reduced to the original Kuramoto, and in this green line, the model is reduced to the Kuramoto-Sakaguchi one.
Is there any reason why Kuramoto is exactly the boundary between the two?
Yeah, because in this, the problem with if you open these two components, you will see that is exactly like in this boundary, because the movement of the in the green region, the system is locked.
Right.
And in the red region, both the module and the phase oscillates. So it starts, for the system to start move, as I go further from this diagonal, more the module oscillates. So it starts rotating exactly in the Kuramoto model because it's only the phase oscillates, and then as further I go from this diagonal, more the phase will oscillate. So it's probably because of that.
The fact that it's symmetric for plus J minus J, it's there is a symmetry, right? The J goes to minus J. It's immediate to see from the equation?
The symmetry is because of this parameter beta. Because in this case is beta equals 0 because this parameter do not have a specific state associated with him, because these two synchronized states are associated with J. K is the original Kuramoto model, and alpha is the delay coupling. But the beta does not have a physical interpretation. It's just to make all things nice. So we usually assume it's equals 0, and then when it's 0, we have all this symmetry. But it's not always that these diagrams are symmetrical. Okay. So here we have some illustrations of which are these new states. We have the phase tune, in which the oscillators, they cluster in a given direction. It could also happen in an angle closer than this, but depending on the initial conditions, they will cluster or in this or in this spot or in this. And the stronger is the synchronization, the lesser is this spreading. They will tend to cluster more and more as I increase the degrees of synchronization of the system. And the oscillatory state, in which I have a direction that the system, they accelerates towards, then they start to rotate slowly and then accelerate. And this spreading, the shrinking and expanding of the oscillators generate a order parameter that oscillates in time. Okay? Well, now I'll discuss a recent work that I developed with my supervisor, Professor Marcos Aguiar from the Unicamp. We expect to have these works published in the next months. which is called Dynamics of Matrix-Coupled Kuramoto Oscillators on Modular Networks, Excitable Behavior and Global Decurrence. Because here we investigated what happened in a system that is homogeneous in terms of interactions. So each oscillator have the same parameter, and we can describe the synchronized state. But what happens if we have certain groups of oscillators with certain parameters and the other groups of oscillators with other parameters? So this is the kind of system that we try to analyze here. We construct a set of equations in a more general possible way with any number of modules, any number of parameters, and then we could not solve because it's too complex. So we reduce the problem in this study, the interactions between these two synchronized states. So we have a module with oscillatory state and a module in the phase tuned, and we investigated how the interaction between these two modules will alter the dynamics of the system. This is what we investigated here, in which we have two modules, one in Kuramoto-Sakaguchi with only K and alpha, and the second one in the phase-tuned state acting as a bottleneck for the whole system. And here we have some heat maps of the order parameter. The brighter, the more synchronized the system was. For the module 1, the module 2, and the system as a whole. The first thing that we can see is an apparent transition that happens in this direction that is related to the Kuramoto-Sakaguchi transition that I showed in the beginning. When I increase the alpha, the delay coupling of the system above a certain threshold, then the system cannot maintain their initial synchronicity. We have this transition here. But what really calls our attention is this, let's say, this black region here, in which we have an apparent system that are initially synchronized with the degree with order parameter around half, and then they simply desynchronize as I increase the parameters. The system, they interact in a destructive way in order to desynchronize the whole system. This quantity does not offer a lot of information, so we calculate the detuning between the modules, which is an interesting metric to measure if the modules have similar dynamics or not. If they have similar frequencies of rotation, it implies that they have similar dynamics. If they have different frequencies, it implies that each module is having their own dynamic. And we can see a lot of different regions here. We can have this, we see this yellow and red region right here, that is in which the detuning is larger, implying that each module is maintaining their own dynamic. And when we analyze the individual trajectories here, the blue is the module 1, the red is the module 2, and the green is the global system. We see that the module 1 is rotating in a let's say a normal way, and the module 2 is just having small perturbations around the equilibrium point, since this module is in the phase-tuned state. So each module have their own dynamics in this region 1. We have this region 2 here, which are characterized by this detuning being 0, in which all the systems are now locked. So the phase-tuned module dominates the dynamic and locks the other module. We can see because of these trajectories. And this black region also appears on the bottom of this figure. It's kind of difficult to delimit exactly where some of those regions start and some of them begin, because this is all numerical. We don't have analytical expressions to try to draw these lines and then to draw these lines. We also have this region 3 here is in more a brown color, in which both modules are now rotating. So the module that is now in the leading dynamic is the module 1. He influences the module that is locked in a way that all the system is now rotating. And the region 4 here, despite not being different from the region 2, is exactly what happens in this small region here. we can see that both their dynamics starts to spiral into zero only on this tiny region here, because the system interacts in a certain way that is in a destructive way, and the whole system desynchronizes. And this is not a region, but it's a curious behavior that we find close to this number 5 here. That is a region that is bottlenecked by the 1 and the 2 here at the bottom. And what we observe in this dynamic, you can see here in this graph, is that despite the system is oscillating, these dots are equally spaced in time, in a way that if you have a more larger density of the dots, imply that the oscillators stay more time in that part of the trajectory. So we can see these preferential positions in the trajectories that the oscillators want to stay, and then they start running to the other position, and then in a mechanism that is closely related to the charge and fire of neurons. So if the system, this behavior is also confirmed if we analyze the instantaneous frequency of each module, in which you have regions in which the frequency is almost 0, and then some spiking, some regular spikings in this system. So we have a system of oscillators that individually they do not act as a charge and fire, as this charge and fire system behaviors like neurons. But when we couple these two modules in a certain way in this region, then the phase tune module acted as a bottleneck, the preferential direction for the whole system, in order to simulate this kind of behavior, despite each individual oscillator not having this neural activation dynamic. Okay, so this is one of the findings of this paper. You can also investigate how some parameters of the system influences the proportion of these regions. In these panels, we vary the J of the module that is phase tuned. We see that for a certain threshold value, that black region vanishes, and then they start to grow. And this case here is really important because it's the only one that we can solve analytically. This white boundary here can be calculated analytically if J equals 0, which is not that relevant because J equals 0 is just a Kuramoto-Sakaguchi case. So that's sad that the only case that we can solve analytically is the only one that was already solved. Okay, so this is another, I will discuss another work that we were investigating concerning. Okay.
An endless game. I mean, you can always add new terms.
Yeah.
What's the motivation for example, now to add this cos of phi?
Okay.
What's the motivation for changing the model and adding new terms?
Okay, we are trying to model increasingly complex systems. So the original Kuramoto model will not present this kind of behavior. So in here we have, for example, this charge and fire that arises in a, let's say, like an emergent dynamic that it could not be seen in other Kuramoto-like models, but it mimics, for example, neurons. And the models yeah. Yes, for example, in this region, there are a lot of particular another order scenarios that this model does not behave as discharge and fire. So this is not an adding ingredient. It's just a result from the model. So we are adding these ingredients in order to try to see new synchronized states and correlate these states with other systems that present these states.
So you try a model, and afterwards you look for some physical system that is described by this model.
Yes,
Okay.
it's a way to think of it. In some cases, you can have some intuition in which what will be the patterns that will emerge for your model, but in a way, you can say that, okay, we add these ingredients, let's see if we have a novel behavior, and if this behavior have a natural phenomenon in which it can be explained by it. And this second case, which I will not detail because of the time, is a similar one. Because now I'm adding two ingredients. We have these matrix coupling oscillators, but now with external drives. We have the same equations that now are non-autonomous, so we cannot eliminate time in this case. And when we perform some integrations, we see these curious stripes that appear in the heat maps that are extremely sensible to the integration of the order parameter. We can see that this border is about 85, and here is 84. So the color difference is extremely sensible, but we can observe this kind of stripes. And when we analyze it, for example, using Poincaré maps, in which we collect the values of the order parameter every time the external force goes a complete cycle, we can see two different outcomes in this case. If we're looking within this stripe, we see a periodic orbit for the system, and we are outside of the stripes, for example, in this reddish region. Here we can see aperiodic orbits. So we can have these different behaviors that can be seen in this kind of system. And when we look for we can see the period of these stripes. You can see that within the stripes we have a low periodic behavior of period 1, 3, 4, 5, and so on. And the white region are the aperiodic orbits, such that this kind of coupling does not occur in the original Kuramoto model, because in the original one, we only have a region in which the system is coupled in one-by-one mode locking with the external force, and the other region in which the system is minding their own business. Here we have a regions of mode lock 1-1, 1-2, 1-3, 1-4, and so on. And this kind of behavior is called the Arnold tongues, and it can be seen in the circadian rhythms that I mentioned in the beginning, in which they try to simulate the segmentation of cells in vitro, and they stimulate these cells with an electrical current to simulate, for example, a short day. If you keep stimulating the cell each 10 hours, for example, then the dynamic of the cell will adjust to this 10-hour stimulation that you put on it. But in some regions, if you set this frequency to certain values, then the synchronization will not be one by one. You stimulate every 5 hours, the cells will divide every 2.5 hours. So you can, this kind of coupling between external force and synchronized behavior can be seen in these in vitro systems, and we can find this kind of behavior here in this kind of models. So it's another example of what Professor Matzes asked in the last question. Okay, this is a more relatively incomplete work, so I will not go into details. Now to the final remarks. I hope to have convinced you that synchronization is a widely occurring phenomenon in nature and in man-made systems. For example, the electric power grid is also a really important system that needs this kind of models, but in this case with inertia to modulate the electric transmission between the power lines. We saw that the Kuramoto model is one of the simplest models to exhibit this disorder to collective motion transitions, and also saw several extensions and generalizations of this model in order to identify these novel transitions and then correlate to natural or other phenomena that occur in the nature. But despite of that, there is still a lot of to investigate, for example, oscillators in which I couple the movement of particles with the oscillator degrees of freedom. For example, the fireflies would be an excellent example of this, in which they move in a room and they also flashes. So we can you need to couple the movement and the oscillation in order to describe this kind of systems. And also higher order interactions are also a very recent and hot topic on complex system physics. So that's it. Thanks for your attention.
Thanks a lot, Guilherme, for this nice talk and this introduction to synchronization. So, questions?
Okay, so I'm not a condensed matter person, so feel free to correct me, but it is my understanding that they have models for example, the magnetization of a magnet, where you have spins which are free to rotate in a sphere in space, and they are arranged in a 3D lattice. Now, I see that the same thing can be done here, right?
Yeah.
Has this been done? Do they recover the fact that you get these domain regions where the spins are all aligned and things like that?
Okay, I believe they have already done this, but it's different because here we do not have the interaction is more simple than an energy interaction, exchange interaction between the spins. So it's just they have their own movement, and this movement, we are not looking on the energy exchanges between neighbors. So I believe it will be different because of this. But I believe they also have done this because it's, for example, an XY model in three dimensions. It's a thing that you can see in a computational physics course in a master or doctorate degree. So I believe they had done this, but not in a theoretical way. I believe. Thanks for the question.
Hi, Guilherme. Thank you very much for the presentation. So I want to talk about space. So you have 1 degree of freedom in your models, which is theta, the angle. Now, if you allow the oscillators to also move in space, then you are going to have interactions which depend on certain ranges of interaction, right? For instance, bacteria, they can have an angle of self-propulsion, which determines the movement of them. And this angle of self-propulsion, they align when they are within some distance. In your case, one of the models has 2 groups of frequencies of oscillators. How do you think space could change this? Because if eventually they become apart, the 2 groups, they would not interact anymore because of space. So it's probably really rich as a model as well, right?
Yeah, the area of formulators which are related to your question is extremely new. And the models that they construct, they usually do not have space in consideration in terms of a volume of the particle, for example. So you have just points that move on a space, but you do not have a self-propulsion in this case, in these initial models. But it could be extremely interesting to model some more realistic formulators in which I have a particle with self-propulsion, and then see which kind of novel behaviors will arise from this kind of system.
Thank you.
Yeah, I have a question. So, what is exactly the dissipation in the Kuramoto model? What is the term that? Yeah. So, in the beginning, you mentioned that synchronization is to some sort of dissipation with environments.
It's due to interaction between the oscillators.
Okay, so only the interaction. You don't need any external mechanism, because in the video you put the cans of soda, and this is a dissipation at some point. So if there is no dissipation, my question is, if you show that the equation of motion for the pendulums that is a system of n pendulums interacting, then you will say, okay, from dynamical systems, that is highly to be chaotic because you have nonlinear interaction and so on. So if that was the case, your flow will cover all the energy, the tori inside the energy shell. And why exactly is the reason? Because, so what is the physical reason why you will have synchronization in which your motion will be in a certain tori and not on the full phase space energy shell?
Okay, I don't know if I understood the question, but I will try to go back to the beginning of the presentation concerning the pendulums, for example. Because the movement of the pendulums are not chaotic in the terms of a double pendulum, for example. They are two pendulums coupled by a support. So it's not, their combined movement, the movements are almost independent. So it's not a double pendulum in this case, you do not have a chaotic movement. So it's easier to understand why they will synchronize.
But if I have any of them,
huh?
if I have many of them and I plot their phase space, you can count the number of, let's say, constants of motion that you will have. And obviously that doesn't let you integrate the motion by quadratures. So that means that you have some kind of freedom in your phase space to move.
Mm-hmm.
So why do you say that it's not chaotic in that direction?
Okay. So these kind of questions are extremely interesting and extremely complicated because, as Professor Matos asked in the beginning, let's say the hard physics of synchronization is not entirely known. Okay, when we can construct these models, we see that this, in fact, happens in some systems. But okay, let's construct Newton equations for the systems and see if we can observe or see in which cases we can have this synchronization. And this is an extremely recent area, and I sadly don't know the answer for your question.
Okay, and small question. So is there any way with the formalism that you show of taking this kind of density of the order parameter and so on to know what is the time that it will take to synchronize?
Yeah, it's possible to extract a transient behavior of these equations, but we mostly have two cases. The first one is the equations are complex enough to not have analytical treatment, so you can, okay, I will perform a simulation and see in how many steps does the system will converge to the stationary states. Mm-hmm. And one interesting example of, let's say, a transient behavior in the circadian rhythms, for example, is those of babies. As babies have the internal clock completely random. So they sleep at random times. They are hungry with random times. They are, let's say, they are in this transient behavior before this synchronization. So you can, for example, estimate what would be the transient behavior for a circadian rhythm in this case. But usually we are not interested in this. We are only interested in the stationary solutions, but it can be done.
More questions? Okay, maybe we can then stop here, and during the tea time we can ask further questions. So thanks again to the speaker.